Let's see if I can figure
I'm going to be in the background on audio and video mute. So
I should be able to share screen here. Is that coming through?
yes, it is.
Awesome. All right. Well, thank you everyone for showing up to my talk today. I'm going to tell you a little bit about the work that's been going on in my lab since 2015 when we started, with a particular focus on what we've done in the last 18 months since we got the GAP funding from the Department of Research and Innovation and FIT. And I want to start off by thanking the college for supporting our work and trying to help us get preliminary data to get these grants funded. It's a really important thing that we all suffer with and suffer through. So it's much appreciated on our end. So what my lab broadly is trying to develop new catalysts, and our catalysts are trying to add a little spice to our design by trying to make them do things that normal catalysts can't do. So in the world of organometallics where I live, there are a lot of transition metals that catalyze various industrial processes, whether they're in pharmaceutical production or polyolefin plastic production or whatever. There's a lot of them out there. And most of the history of transition metal chemistry has studied what these metals do in isolation. So when you make a catalyst, if you want to have ultimate control over it, you put the metal in the middle of a bunch of organic stuff and you let the metal function essentially independently within this big framework. And in a lot of ways, this is stolen straight from biology. If we think of enzymes as being a transition metal stuck in the middle of a big protein, that's one way to look at what a biological system is. Now, what we want to do in my lab is take, oh, you guys are seeing presented?
Yeah, I was just about to jump in there when you transitioned and say, can you change your display settings if you don't mind?
Better?
Yes, perfect. Thank you.
Awesome. Sorry about that.
No worries.
Anyway, what we want to do is add some extra components into our system that allow the metal to do more than it can do by itself. And so the first project I'm not going to talk about today, but it's one that my lab has been working on for a couple of years, tries to exploit the organic stuff around the metal to direct reactivity to bonds that don't want to react. And this is really important in pharmaceutical synthesis and production, which is how we got some money from the NIH to work on that. And I'd be happy to talk to anyone about that project afterwards if you're interested in it. We're starting to get some really cool results just within the last month or two on that. And I'm more than happy to talk about that project. The project I am going to talk about today was the one that was part of the GAP funding, uses aluminum-based ligands as pendant Lewis acids. And so what we're trying to do is construct a catalyst that has two metal centers, a late transition metal and an aluminum site. This aluminum site is there to serve as an acidic portion of our molecule, and acid is known to accelerate a lot of catalytic processes, and so we thought that aluminum would be a particularly good choice. It's a very, very strong acid. Our motivation for aluminum came largely from our initial research thrust back when I was drawing up job proposals to try to activate carbon-oxygen bonds. And so if we want to look at our alternative chemical feedstocks, things like lignin or carbon dioxide, which are very, very difficult to get to react productively, you need to break a carbon-oxygen bond. Aluminum has a lot of affinity for oxygen, and so we thought that it would be an ideal candidate to serve as a promoter within our catalyst structure. We were not the first people to have this idea of putting a Lewis acid into your transition metal complex. When I was first, again, getting into this area, there had been quite a bit of work using boron, which in the periodic table is aluminum's next neighbor. And some of these systems from Jonas Peters at Caltech or Josh Figueroa at UC San Diego used a late transition metal and a boron center to activate carbon-oxygen bonds, carbon-nitrogen bonds, and a little bit of hydrogen gas, some catalytic stuff with hydrogenation. But overall, the field was quite small. And I was thinking why people wouldn't use aluminum. It's a stronger Lewis acid. It seems like that should be a benefit. And sure enough, just as we got started, in early 2016, Didier Bourriceau in France published one of the first late metal aluminum systems that was capable of activating bonds. I'll pay special attention to these two here on the bottom, as these are actually catalytic systems. The system from Iwasawa and Takaya catalyzed the reduction of carbon dioxide via hydrosilylation at one of the fastest turnover frequencies known in the literature. So this is a really excellent catalyst. It goes at like 19,000 per hour, which is really, really fast for this type of reaction. And if you're trying to use alternative feedstocks, you need a catalyst that operates very quickly. Otherwise, your value added product is not going to get you much value. So this was really promising for us. Unfortunately, when we started, none of this was in the literature, and we had much simpler goals when we got going. The first goal was, how do you actually make a transition metal aluminum bimetallic? There were scattered examples, maybe 10 in the literature when we started, and they were all made in kind of specific, unique ways that wouldn't be extendable to other systems. And so if we want to develop a catalyst and then optimize said catalyst and get it to do a whole bunch of things, we need to be able to synthesize these in a reliable way and in a modular way so that we can swap out components without having to redesign the entire synthesis. So that was kind of the first goal that we set for the lab, was figure out how to make them. Second, we wanted to be able to interrogate the systems that we make, and so that as we go to modify them, we're modifying them in a rational manner. And then finally, we're going to react them with some small molecules. I'm actually not going to talk about the small molecule reactivity today because it's kind of outside the scope of what we were looking at for the GAP funding. But long story short, it works. They react with small molecules. So we are not wasting our time here. The synthetic strategy that we finally settled on is somewhat backwards from the way that generally transition metal chemists operate. Usually, as a transition metal chemist, we will assemble all of the organic components together and bring in the transition metal at the very end and say, yay, we made our compound, and throw a party or something. But in this case, that doesn't really work, because the reason that you do that normally is that the transition metal is the most reactive thing that you have. It's the hardest to control. But in our system, that's actually aluminum. It's not the transition metal. Aluminum reacts with anything that has an OH bond in it or an NH bond in it, and very, very quickly. So the aluminum precursors that we're using, which are aluminum alkyls. And so we thought, let's bring the aluminum in the last. It's going to be the most reactive thing. And so we designed a whole bunch of transition metal compounds that have these dangling OH groups. We can bring in our aluminum alkyl, so like a butyl group, and that will remove the H atom to make butane, which bubbles out. It's the gas in your lighters. So we know that that's a nice gaseous thing, which makes purification really easy. And then we get our final compound. And as we developed this synthesis, we thought, well, let's actually be even smarter about this and not just use any random transition metal component. Let's use a transition metal component that can give us the electronic information we want. And so we settled on compound 1 here, which is Bosca's complex, known colloquially. It was developed in the 60s by a guy named Bosca at Carnegie Mellon, and has borne his name ever since. And it has this CO group on it, which serves as a handy electronic reporter. And so when we get done making our bimetallics, this CO will still be there. And so we can just measure its vibrational frequency, and that can tell us a lot about the electronic system that we have, which is a really nice thing. The other beauty to Bosca's complex is it's really easy to work with. We can make grams of the stuff, which is great. So we can take this and we can swap out for a bridging ligand that has that dangling OH group on it. And here's a crystal structure of the rhodium variant. And if you react that with aluminum, just as we predicted, you boil off your alkane and you make the bimetallic structures that you want. Now, we do a lot of our characterization in my lab by NMR spectroscopy, which in this case is the perfect way to look at these molecules. We can predict what the spectrum will look like, which is shown in blue, and we can actually measure the spectrum, which is in black, and based on prediction and measure matching up beautifully, we know a lot about our system and what it should be. We also are able to look at the solid state structure of this using X-ray crystallography. This was done by my friend Nate Schley at Vanderbilt on his instrument. Though the chem department here just got a single crystal from the NSF, which I'm very X-ray diffractometer from NSF, which I'm really excited about being able to do this in-house. Anyway, we can get the structures and get the nice snapshot pictures. And I'll point out one thing that's going to come back later, and that's that these two metals, so the aluminum, which is shown here in pink, and our iridium center, which is shown here in blue, are about 5 angstroms apart from each other, which is a really long way. So just file that in the back of your mind. They're far apart. Okay. So we thought this was great, and we published this. This was the first paper from my lab, came out back in 2018, and kind of provided the groundwork for everything that we've done in this area since then. As we started looking for funding opportunities, it became clear that we needed to expand our repertoire and make a whole bunch of these and see that the electronic effects are real. So we investigated what electronic effect the component bridging in the middle would have. If we change the alkyl groups on aluminum, what's that going to do? If we change the anion from nitrate to something else, what's that going to do? And thankfully, we have a nice modular synthesis, just as we designed it, and we're able to make all of the various variants that we want to make, get beautiful crystallographic pictures of them. We can use more extensive bridges like these hydroxyquinolines. And this is about where we were when I applied for the GAP funding from the university. What we still needed to do was come up with an application for this, which is important, and also to measure and catalog all of the electronic effects that we have. And so we did that. We made a giant electronic table, and I'm not going to bore you by going through this table. I just want you to bask in its glow of how nice and rich and full of data it is. The only thing I'm going to say about this is that all of these numbers are different. And so as we make changes, whether it's in the bridge or in the functionality on aluminum, we see changes. Now, 5 angstroms away, seeing a change that is being caused by the aluminum onto the iridium, I said that's really far. That's really far. That's not that common to be able to do. So this is a pretty unique system that we've stumbled upon. And so the big question is, what can we do with this? And that's what the purpose of the GAP funding was, is to try to figure out what we can do. So in our mind, the first thing we thought of was, can we use this and modify our system so that it functions as a switch? So there's an entire field of what we call switchable catalysis, where you have a catalyst that can exist in multiple different states, usually 2. And one state, it reacts, and in the other state, it doesn't. So we have an on-off switch. So an example of that is shown here. This is from the lab of Paula Diaconescu at UCLA, where she has this iron component in her catalyst, and it can be either orange like this when it's in an iron 2 oxidation state, or it can be green when it's in iron 3. And if you switch it from iron 2 to iron 3, depending on what metal you put in there with it, you can turn on the catalyst at the metal or off. So if the metal is yttrium, the iron 2 is on and the iron 3 is off. If it's indium, they switch. But the point is, they have control over what the catalyst does. This is also really convenient because you can switch it in the middle of a run. You can turn it on, you can turn it off, you can see what's going on. Now, the field of switchable catalysis is not a new field, but what would be kind of new and what would be kind of cool would be if we had a switch that did more than an on and off thing. If we could install what I like to call a dimmer switch into our molecule, that would be really cool. So if we change our aluminum component, we know that's going to change the electronics. And if we make this thing redox active to where we can add electrons and take electrons away, that's going to change its electronic properties, and that's going to change what the catalyst does. Now, the beauty of doing this with aluminum is that you can design your system so that it can exist in 2, 3, 4, 5 different electronic states with one catalyst structure. And so you can get to this multi-state or dimmer switch concept that we want to do. So I think we have the groundwork to be able to do that. Now we just need the application. Well, the application that we've chosen to work with is plastics, and specifically looking at polyolefins. So polyolefins are the largest produced plastics in the world. Polyethylene and polypropylene make up more than half of the tonnage of plastic that's produced annually. We're talking billions and billions of tons of these produced every year. They make up everything from your bottles to food containers to toys to carpets. When you go and recycle stuff later, if it's got the PP in the little triangle, it's polypropylene. If it's HDPE or LDPE, it's polyethylene, or just PE is polyethylene. And I guarantee you, if you look at your bottles later, you'll see it. Now, what's difficult about polyolefins, of course, is that they don't break down. They last essentially forever. The environmental impact and all of that is becoming a real problem. And so one of the problems that one of the things people are trying to do is install polar groups into your plastics. Now, polyolefins, polyethylene, and polypropylene is all carbon and hydrogen, and so these tend to be what we call non-polar. They don't interact with much, they're hard to break down. But if you put something polar in there, then all of a sudden you've got something that can interact with an external catalyst or something that comes in and can help degrade your polymer. It will also cause stronger adhesion. So if you're trying to stick it to a surface, that would be really nice. You might be able to cross-link your polymer and actually make stronger polymers if you want that. You could dye them a little bit easier. Most dyes are polar, and polar things like polar things. And you're also going to change the solubility of your polymer if you can put polar groups in it. So you might be thinking, why haven't I seen polar polyolefins regularly? Well, the answer is because you can't make them using the normal industrial catalysts. The catalysts are trashed by the polar substrates. So if you want this to happen, you need to have a different catalyst. And people have been working on this literally since the 1950s, when the first plastics, polyolefin plastics catalysts were discovered at Chevron Phillips. So what we want to do is take this one step further and take what is known in the polar functional polyolefins literature and attach a redox switch to it. So we need to design this catalyst, and then we need to look at the electronic states to see if this happens. So the known catalysts that are out there for using, for putting polar groups into plastics are based on two main frameworks. You've got this framework of Burckhardt, where it's usually nickel in this bisamine type thing, or you have the system of Drent, Nozaki, and Chen, where it's usually palladium bound to a phosphine and then some weakly bound other ligand. Now I'm going to focus specifically on the Nozaki and Chen ones because these are particularly relevant to what we're trying to do, because they look like the easiest ones to attach an aluminum to. So if we take the Nozaki and Chen catalyst base and then we just add in a little oxygen on the back so we can stick our aluminum, then the synthetic route that we had developed in the lab is going to work to make these bimetallic systems. And if we're really smart about the aluminum things that we choose, then we can make them redox active. The aluminum centers that we've chosen to work with were developed in two different labs. This aminopyridine was developed in the lab of Louise Bourbon at UC Davis. And this, what we call Pino, was developed in the lab of Chris Graves at Swarthmore College. And so I called up Chris, who I've known for many years, and asked him if he wanted to work with us on this. And he said that he would love to. And so he has been, his lab at Swarthmore, making us this redox active ligand, or at least they were until COVID shut them down. But now that they are starting to get back up and running again, hopefully this summer they will resume their production capabilities. And these aminopyridine and PDI based ligands are being synthesized for us by my collaborators at Centre College. It's a good undergraduate research project. It's pretty worked out. So I'm not going to dwell on it here, but we've decided to work with these fragments. These fragments were chosen because they function differently. The Pino one, you can take electrons out of, and so you can make your aluminum more electron poor, which should make your ligand a weaker donor. The aminopyridine, you can add electrons in and it should make it a stronger donor. And this should gives you a much broader tuning range than we would have otherwise. So what our lab has been working on is trying to figure out how to make the bridge and make sure that we can dock the aluminum. So I've shown here the synthesis of the bridging ligand. This was designed by Natalie Taylor, who's a grad student in my group. And she's been working on this for a while. This isn't the first thing we tried, but it's the first one that looks like it's going to work. And so I won't bore you with all of the organic chemistry here, but suffice to say, it's a multi-step process, but it's actually pretty high yielding, and none of these reactions are particularly long. So we can get from the starting point to here, this phosphine oxide in about 2 days. And it's now that we know what we're doing, it's not too bad to do. We expect to be able to extend the synthesis out and make the other derivatives that we had proposed in the near future. The most important piece that was discovered during the GAP funding time was that our docking protocols for making these bimetallics actually extends to these redox active species. So undergraduate Michael Cheney, who was working with me last summer, figured all of this out using our Vosca's complex derivatives, because this is what we were working with at the time. He was able to take the Vosca's complex derivative, modify it by removing the proton, bring in the aluminum precursor, and assemble this bimetallic where we've got our late transition metal and our redox active species. This is the mass spec of this, so it's exactly what we think it is. Right as the summer was ending, we were able to finally obtain this, and we are now in the process of figuring out how to purify it and get it all good. Progress has been a little slower than I wanted it to be because of COVID and its complications, but nonetheless, I feel like we've made some pretty good progress at trying to get some of this data, and we've got the proof of principle that we can make the compounds that we want. So with all of that being said, what's left to do? The answer is a lot. We need to assemble the catalyst, we need to test it, we need to do the electronic studies, basically everything that we would want to do in the grant that we are applying for. We need to just continue to assemble the preliminary data on this. And I'm hoping that by the end of the summer, we will have at least one of the catalysts made and tested, given that my collaborators are also ramping back up their research activities. I think we're in pretty good shape here to be competitive for funding for this project in the fall. So with that, I need to acknowledge several people. First, I need to acknowledge the University of Memphis, specifically Research and Innovation, for giving me some GAP funding to help us get this data, to bridge the gap between our simple bimetallics and this way more complicated system that I'm really excited about, and that's going to be pretty nicely fundable. I also need to thank the students who worked on this. I've bolded them here, Malcolm, Angel, and Natalie. And then undergrad Michael, who I highlighted at his point in the talk. I need to thank my collaborators around the department, Nate DeYonker and his student Hirschkesh, who do some computational work for us, Will Eckenhoff over at Rhodes, who does some electrochemistry, and then Nathan I mentioned, who does some crystallography. The computation and the electrochemistry were instrumental in putting together the massive data table that I didn't talk about, but nonetheless really important. This is my lab right here. I need to thank all of them. They're great people. I need to thank you guys for being here and humoring me for the last 20 minutes, and I'd be happy to take any questions that you have.
Thank you, Dr. Brewster. That was great. If there are any questions, please go ahead and speak now. It looks like Malcolm is with us, so I promoted him to a panelist and was able to let him on this side of the what do you call it? The webinar. Excuse me.
I have a couple questions for my boss, but if anyone else has questions, they can go first.
No, go ahead.
Okay, so on slide 20, I saw that you and Michael got MS. Do we have NMR of this complex at all?
Yes.
Outstanding. Have we only made it with, and by we I mean you and Michael, made it with just the hydroxyquinolines?
Yeah, so we used the hydroxyquinoline, so that's this piece in the middle for those scoring at home. We used the hydroxyquinoline because we thought that this would be the best mimic for how far away the aluminum center was going to be from the transition metal and the final things that we made. And also we used it because we thought that that would eliminate the steric interaction between the aluminum and the iridium, because this pino thing is pretty clunky. And we wanted to give ourselves the best possible chance of making it. So yeah, that's the only one we've done.
That also answered my follow-up question, like why didn't we use just the purity and stuff? But that makes sense. It pushes it further away. So
yeah,
cool. Thanks. Great talk.
Thanks.
Thank you, Charles. Sorry, thank you, Malcolm. Doesn't look like we actually have any other panelists on board or attendees, unfortunately. So if there aren't any more questions, I think we can go ahead and end our session here.
Thank you for letting me talk today.
All right. Thank you much. Thanks for attending. All right. Thanks all. Bye-bye.